Imagine trying to build a delicate sandcastle on a vibrating table where every grain of sand is constantly shifting and disappearing. This is a bit like the challenge facing scientists working with quantum computers. What complicates error management in quantum algorithms are primarily the extreme fragility of quantum information, the nature of quantum errors themselves, and the current limitations of quantum hardware. Unlike classical computing, where errors are usually clear bit flips from 0 to 1 or vice versa, quantum errors are far more subtle and pervasive. The core reason for this complexity stems from the very principles that make quantum computing powerful. Qubits, the basic units of quantum information, can exist in superposition, meaning they can be both 0 and 1 simultaneously, and they can be entangled, meaning their fates are intertwined. However, this delicate quantum state is highly susceptible to interference from the environment, a phenomenon known as decoherence. When decoherence occurs, the quantum information rapidly degrades, making it incredibly difficult to maintain a stable computation. Furthermore, quantum errors are not just simple bit flips. They can also involve phase errors, where the relative phase between the quantum states changes, or even combinations of both. These complex error types mean we cannot just detect and correct them in the same straightforward way we would a classical bit flip. This means that simply isolating quantum systems from external noise, while crucial, is not enough. We need to implement sophisticated strategies like quantum error correction codes. These codes work by encoding a single logical qubit onto multiple physical qubits, creating redundancy. If one of these physical qubits experiences an error, it can be detected and corrected without directly measuring the fragile logical qubit, which would destroy its quantum state. Think of it like spreading a secret message across several envelopes, so if one gets damaged, you can still reconstruct the original message from the others. A key concept here is the fault tolerance threshold. This refers to the maximum error rate per quantum gate operation that a quantum computer can sustain while still being able to perform reliable computation using error correction. Achieving this threshold is one of the biggest hurdles in building large-scale, useful quantum computers. Scientists are pushing the boundaries of hardware design and developing innovative coding schemes to overcome this challenge, exploring architectures that minimize interactions with the environment and increase qubit stability. These efforts are crucial because every step towards reducing errors brings us closer to unlocking the full potential of quantum algorithms. Ultimately, managing errors in quantum algorithms is a monumental task that requires a deep understanding of quantum mechanics, innovative engineering, and advanced theoretical computer science. By continuously improving our ability to protect and correct quantum information, we pave the way for a new era of computation, enabling solutions to problems currently beyond our reach, from designing new materials to discovering life-saving drugs.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.